So our video got cut off. P and Q are constants here. So P and Q, P divided by Q is going to be another constant, which is kind of redundant, but for our purposes, it's going to do as well. We're going to divide both sides of this equation, BQ equals VAP, by Q, and we're going to define our P over Q as K. And this becomes an important part here. P dx squared. So our invariant interval, it will be rewritten as P ds squared equals Q dt squared plus K dx squared. And when you plug this into these, it's still going. And when you plug this into these equations end up being all the same. They end up being kind of redundant. So that leaves us with this equation: a plus avb equals 1, and some constant k. Well, we can replace b with v squared a squared equals, or a squared times 1 plus k v squared equals 1, and that means that a equals 1, or the square root of 1 over 1 plus kv squared. That checks out. When you switch the direction of the velocity, it doesn't change anything good. Doesn't change anything. So our Lorentz transformations can be written, and then b is 1 over 1 plus kv squared VAK. So our Lorentz transformations can be written, I'm down here now, can be written as x prime t prime equals, okay, so x prime equals 1 plus kv squared x minus vt, and 1 over 1 plus kv squared t plus vkx equals t prime equals x prime. And I'm going to rewrite, those are our Lorentz transformations. So we don't need all this anymore. This all could have been simplified if you brought up well, disregard that line. Still good? Still going? Alright. I'm going to write up here our Lorentz transformations. X prime equals, and I've done this all in 1D, there we go. Those are our Lorentz transformations up there. And our invariant interval is ds squared equals q dt squared plus k dx squared. It's our flat space distance between points in space-time, basically. Events in space-time, I guess, is the more formal jargon. This last step here is the most hand-wavy part, but I mentioned it kind of crudely earlier. The idea that if Carl, the object that Bob and Alice are observing, just for another example, is moving at the same speed as Bob, so x prime will be 0, as we said. That means that t equals t square root of 1 plus kv squared, 1 plus kv squared times t. That's just cancels out because that's that squared, so you get the square root on top now, t. That hand-wavy idea that in that situation, time can only dilate. It can't get bigger. For some reason, that appears to be a fundamental property here. I have some ideas, but I'm not going to share them right now. Has to be less than the time coordinate in the rest frame. So the time coordinate in the moving frame, motion's not going to make your time coordinate be greater than that in the moving frame, which is the most hand-wavy part of this, but it has very much importance because you can cancel out t in this inequality here, less than 1, square both sides, that's just going to be 1, subtract 1 from each side, that's going to be less than 0. Velocity squared, velocity is a real number, so it's positive. Still on? Yeah, so it's positive, which means that k has to be less than 0. And that's a big thing here, because k is, we can now write -1 times the absolute value of k equals k. It's a negative number. Well, in this factor here, 1 plus kb squared, there's now 1 minus absolute value k. There's now a special speed, and we'll call it c, where this factor, if you exceed that speed, this will become imaginary valued, which is very unphysical, and if you get to that value, it'll go to 0, which is dividing 1 divided by 0, and will blow up to infinity and non-defined stuff. We call that speed c, and that's the speed of light in a vacuum, as it's more famously called. So we're going to redefine 1 over c squared equals the absolute value of k, and negative that to get k. We're going to rewrite these now. K equals -1 over c squared, the special speed that's the same to all inertial observers. Now see, if I had started with that idea, this would have probably been chopped down a lot, but I kind of like to build things from as few principles as possible. But the one I used was pretty hand-wavy, so I just think that's fascinating. That big thing in physics can be is not, it might not really be that fundamental, but more derivable. So here's our Lorentz transformations, and we'll replace k there, -1 over c squared. We're going to just write, because it doesn't really matter, it's just a factor, c squared equals q, so we can get units, our interval in spatial units. And so here's our results here. In a flat space-time, and this generalizes here because our y and z coordinates weren't changed. You can actually generalize this to 3 space coordinates, of dx squared, dy squared, dz squared. So our Lorentz transformations here are this, the Lorentz factor, x minus vt, Lorentz factor t prime equals that times t plus -v over c squared x. And our invariant interval in the flat space-time is equal to c squared dt squared minus the sum over the x coordinates, dy squared. And an interesting thing about this is, in ordinary space, that would be our Pythagorean theorem, and it'd all be positive. The coefficients are all positive. But in space-time, our coefficients are negative in this metric. Well, in either one, you could do positive and do negative c squared if you wanted to. It's a redundancy, it's just a different signature. But is negative. The time components are negative to the spatial components, which is fascinating. But anyway, that's our results here. Our interval is this, and our Lorentz transformations are those right there. Pause. We're good.